welcome to CEC lectures. Myself Dr. Priti Jagwani from Department of Computer Science, Arbit College, University of Delhi. So in this present series of computer networks, in the previous lectures what we have completed is actually we were dealing through data link layer, and within the data link layer we looked into two of its sublayers, one which is MAC layer and another one is LLC layer. And going forward we are going to look into multiple access protocols, which is actually kind of related to channel allocation, and this channel allocation is the responsibility of your MAC layer. So in this way this thing is connected to data link layer. Now when we talk about network links, they can be divided into two categories. One which is point to point connections, and another one which are using broadcast channels. So in point to point connections there is kind of no issue when we talk about the communication or the use of channel, or basically if we want to determine who is going to get the channel for the communication. So if it is a point to point link between kind of two ends, or we can say a sender and a receiver, there is no problem. But as far as broadcast network is considered, the key issue is how are we going to determine who is going to get the channel next, or who gets to use the channel when there is a competition for it. So when only a single channel is available, it is going to be much harder to determine that who should go next. And for solving this kind of problem, there are so many protocols which are available in order to solve this problems. And these broadcast channels are sometimes referred to as multi-access channels or random access channels, and hence the topic for today was named as multi-access protocols. So the protocols which are used to determine who goes next on a multi-access channel belong to the sub-layer of data link layer, which is the MAC layer, medium access control sublayer. So this is this is the responsibility, or for kind of looking into all these protocols comes under the prerogative of MAC sublayer. MAC sublayer is especially important in our local area networks which are LANs, particularly the wireless ones, because wireless is kind of a broadcast channel, or we can say it is kind of a natural broadcast channel. It is naturally a broadcasting medium. So your MAC sublayer becomes especially in wireless LANs. WANs in contrast use point to point links except for the satellite network. So in case of LAN, our topic becomes kind of more prominent, more important. Now this problem is, how are we going to allocate a single broadcast channel among various, or we can say among many competing users. The channel, it could be a portion of wireless spectrum in a geographic region, it could be a single wire, it could be a single optical fiber to which the multiple nodes are connected. So how many nodes are connected, that actually does not matter, but the channel, what kind of channel could be there, as I have told you, a portion of wireless spectrum in a geographical region, maybe a single wire or an optical fiber connected to multiple nodes on both the ends. In these cases, the channel connects each user to all other users, and any user who make full use of the channel interfere with other users who also wish to use the channel. So, for example, here we have 4 nodes A, B, C, D, and at the other end we have 1, 2, 3, 4. So, let us say A is communicating to 3, then kind of if it is making full use of the channel, that, and if 2 or any other let us say B or C wants to communicate to other users at the different end, it is going to kind of create an interference. So, there is going to be a competition among the users who wish to use the channel. So, this is what the situation is, and we are going to look into what kind of protocols we have in place in order to solve this kind of situation. So, basically here If we talk about one scenario which we can say is an static channel allocation, so solution could be kind of FDM or TDM, and as you are aware, this FDM is frequency division multiplexing, TDM is time division multiplexing, and so on and so forth. So basically, in the scenario of a static channel, the traditional way of allocating a single channel, that channel we can kind of take as an example such as a telephone trunk. And if that channel is to be allocated among various users, among multiple competing users, so FDM says, or even time division multiplexing TDM says that we need to chop up either the capacity or the time by using one of the multiplexing schemes. So, in case of static channel allocation, multiplexing schemes can be an idea or can be an solution here. But what happens when there will be number of senders, and that number of senders will become very large, and it is also kind of not fixed, it is varying, and the traffic is also bursty. So, I hope you understand that traffic is bursty in the sense that at one point of time huge amount of traffic is coming, and at the another point of time it is kind of a lean period or it is a silent period kind of thing. So, in this situation, when the number of senders is large and varying, or even the traffic is bursty, your FDM is going to present some problems. Now, what kind of problems? Let us try to see that. So, if the spectrum is cut into n regions, and assume that n users, or we can say fewer than n users are currently interested in communicating. That means many of the pieces, or many of the kind of regions are going to be wasted, or we can say a large piece of valuable spectrum will be wasted, because we have allocated, or we have cut the spectrum into n regions, and fewer than n users are interested in communicating at a particular point of time, obviously. So, at that time a large piece of spectrum is going to be wasted, and hence it is not the efficient technique of this channel allocation, we can say. There could be another situation, which is we can say is another side of this coin, which says if what if more than n user wants to communicate, and you have only kind of n pieces of that spectrum. That essentially means that some of them will be denied permission for the lack of bandwidth, obviously, and even if some of the users who have been already assigned a frequency band, hardly ever transmit or receive anything. So, to whom we have given, are they using it properly, and what about those who are not going to get their share of spectrum? So, in this way, as the traffic is varying, your FDM or these kind of multiplexing schemes are going to present a scenario in which the spectrum is not completely and efficiently utilized. Also, so this was the scenario when your number of nodes are varying and they have large number of nodes. Another scenario when your kind of traffic is bursty. So, in this situation again a static allocation scheme is going to be a poor fit. Why it is going to be a poor fit? Because when your data traffic is extremely bursty, often with the peak traffic to mean traffic ratio is thousands to 1. So, let us say 1000 units of traffic are being passed at one point of time, which is kind of the peak scenario, and let us say the mean traffic scenario in which only 1 unit of kind of traffic is passing on. So, what is happening with these kinds of skewed ratios, which is kind of 1000:1, that means your data traffic is extremely bursty. Then also this static channel allocation is going to give you a problem. So, because of these kind of situation, of these peak traffic scenarios or bursty traffic scenarios, your most of the channels will be idle most of the time. So, both the scenarios, with the large number, with the varying number of nodes, or even in case of bursty traffic, static channel allocation is not at all good fit. So, even none of the traditional static channel allocation method is going to work well with all that bursty traffic. So, what do we need to do? So, we need to use some dynamic methods. So, we need to look into this dynamic channel allocation. So, before going into this dynamic channel allocation, we will be looking into what are the assumptions of this dynamic channel allocation. So, the first assumption of dynamic channel allocation is the traffic independency, which is independent traffic. Independent traffic says the model consists of n independent stations. These stations could be computer, telephones or whatever, each with a program or with a user that generates frames for transmission. Then the situation comes up that what is going to be the expected number of frames generated in an interval. So, let us say the interval is of length, assuming it is kind of delta t, and lambda is a constant, and so the expected number of frames generated in an interval of length delta t is lambda into delta t, where lambda is a constant, which is this constant is the arrival rate of new frames. So, whatever new frames are being arrived in a particular interval of length delta t, that is going to be the expected number of frames generated, which is lambda into delta t. So, this says the traffic is independent, in the sense once the frame has been generated, we can say further the station is blocked and does nothing until the frame has been successfully transmitted. So, traffic is independent of everything everything else. That is the first assumption of is dynamic channel allocation. Moving further, the second assumption or the next assumption is there is a single channel which is available for all the communication, and hence it is known as single channel communication, and all the stations can transmit on it and can receive from it, but there is going to be a single channel. If we kind of remove this kind of assumption of single channel, our problem will be solved. If there are kind of multiple channels between many nodes, we do not have any we do not have much of the problem. So, single channel is the availability of the single channel for the whole communication is also an kind of assumption through which or under which we are going to work into the dynamic allocation schemes. And all these stations can transmit on it and can receive from it. Now, stations are also assumed to be equally capable through protocols, though protocols may assign them different roles. So, all these stations are assumed to be equally capable. That means all the stations are going to transmit, or we can say they are having the capability to transmit kind of a similar number of frames. So, it is not like that one particular station is going to generate less number of frames, another one is going to generate a higher number of frames. So, the assumption under which we are working is all these stations are assumed to be equally capable, although there are scenarios in which protocols may assign them different priorities. For example, under a particular protocol, your station A is going to have a priority for sending or kind of for transmitting the frames as compared to the station B. That scenario is possible, but that really does not mean that station B is not equally capable as that of A in frame generation thing. So, that is another assumption. Then the next situation is it is about collisions. So, collisions means, so collisions basically says when there are two frames on a single channel and they are transmitting within a particular time frame, they collide with each other and the data is kind of we can say go into wastage or discarded. So, the next assumption is about observable collisions. So, observable collision says if two frames are transmitted simultaneously, they overlap in time. So, the resulting signal is garbled. That means, as I have told you, that it goes into the wastage. This event is called a collision. Now, when we talk about observable collision, that means the stations can detect that a collision has occurred, and even all the stations have this capability of collision detection. Then in order to complete the transmission, a collided frame must be transmitted again in the later course of time. So, it is not like that one particular frame is collided to another one and then we just discard the frame and do not retransmit it. So, that retransmission has to kind of happen in order to have the whole data at the receiving end. And also we are assuming that there are no errors other than those generated by collision error. So, if it is a collision, then your resulting signal is going to be garbled, but other than this we are assuming that there are kind of no other errors are there on this in this whole transmission process. Moving further, another assumption is about continuous or slotted time. So, time may be assumed continuous, in which case the frame transmission can begin at any instant at any point of time, because the time is assumed to be continuous. Alternatively, we can say that time may be slotted or time may be divided into discrete intervals, and these discrete intervals are known as slots. Now, what is the kind of we can say utility of these slots? So, that means the frame transmission must then begin at the start of a slot. So, if it is kind of continuous times, that frame transmission can begin at any instance. If it is kind of slotted time or divided into discrete intervals, which are more commonly known as slots, in this situation your frame transmission must then begin at the start of the slot. So, a slot may contain 0, 1 or it could be more frames. Corresponding to an ideal slot, a successful transmission or a collision respectively. So, basically a slot may have 0 frames, it may have 1 frames or even it may have more frames. So, having a 0 frame corresponds to an ideal slot. That means that slot is not transmitting, or within that particular slot no frame is being transmitted. If the slot is having 1 frame, that means this slot is going to have a successful transmission, because other than collision we have already assumed that there are no other errors except the collision. Or even if within a single slot there are more frames. So, these more frames actually corresponds to collision. So, within a single slot, if it is 0 frame, slot is idle. If it is 1 frame, it is going to give us a successful transmission, and if there are more frames, that means there is going to have happen a collision. So, this is what it is. Another capability or another assumption with your kind of these dynamic channel allocation is it could your this it can have a capability of carrier sense or no carrier sense. So, what is carrier sense or no carrier sense? So, with the carrier sense assumptions, stations can tell if the channel is in use before trying to use it. That means the stations can sense the channel, that whether a frame is already transmitting onto that particular channel or not. So, that means stations can tell if the channel is in already is in use, or the channel is we can say busy before trying to use it. That means they are able to sense the carrier, and obviously if already the channel is busy, or we can say the channel is in use, that essentially means that no station will attempt to use the channel which is already kind of sensed or marked as busy, because then there is no point in sending the transmission or sending the frames, because this will result in collision. So, if a station has kind of sense that channel is busy, that means it will not attempt to use that particular channel. Now, another situation could be of no carrier sense. So, no carrier sense that says that stations are not able to sense the channel before trying to use it, or we can say stations are not capable of sensing the channel before trying to use it. So, in this situation, any station or any node, we can say they just go ahead and transmit. Only later can they determine whether the transmission was successful or not, or whether their frame has got into a collision. But initially, in case of no carrier sense, they are not able to kind of judge, they are not able to sense that whether the channel is busy or already in use, and thus in this situation they just go ahead and transmit. But later, yes, in case of collision, they are able to kind of determine, they are able to detect that a collision has kind of already happened. Now, all the multiple access protocols which we are going to look into soon, basically we can say what are these multiple access protocols. They are actually a set of protocols, as I have already told you, that they are operating in MAC sublayer, which is medium access control sublayer of the open system interconnection model, and these protocols allow a number of nodes, or maybe we can say a number of users, to access a shared network channel. Several data streams originating from several nodes are transferred through the multi-point transmission channel. Now, what is going to be the kind of literal objective of these multiple access or multi-access protocol? So, the objectives of these multi-access protocols could be optimization of transmission time, obviously minimization of collision, so that retransmissions can be prevented, and also the avoidance of crosstalk. Although we have not kind of described crosstalk as one of the we have not discussed this crosstalks under the assumption, but still avoidance of crosstalks, minimization of collision, and hence kind of increasing the efficiency by saving the retransmission time and so on and so forth are there on the agenda, obviously. And then optimization of transmission time these are the objectives of multi-access protocol. So, when we look into all those multi-access protocols, these are basically divided into three categories. So, one is random access protocols. Under these random access protocols, we have Aloha, then we have SASMA, we have SASMA CD, and we have SASMA CA. Obviously, we will be looking into not only the full form, but detail of all these protocols in our upcoming lectures. The second category is about controlled access protocols. So, these controlled access protocols actually are reservations, then polling, or it could be token passing. Then another category is about kind of channelization protocols. Within the category of channelization protocols, we have all those multiplexing schemes which we were talking about, which are kind of FDMA, then we have TDMA and CDMA. All these kind of multiplexing techniques are there under channelization protocols. So, basically three categories of protocols under these multiple access protocols. One is random access protocols, another one is controlled access protocols, and third one is channelization protocols. So, yes, we will be looking into kind of what all these protocols mean to a user, And then of course we will be kind of taking at least these random access protocols, which are Aloha, SASMA, SASMA CD and SASMA CA, in our in quite a greater length of detail, because these protocols or these MAC sublayer protocols are actually a very important topic when we consider our computer networks as a paper. So yes, definitely we will be looking into all these things. So in this lecture what we have looked into is your what is actually these multiple access protocols, what are the kind of problems with this channel allocations, what are the kind of, we can say, assumptions for dynamic channel allocation, and so on and so forth. Definitely we will be looking into other kind of all these categories of multiple access protocols in our upcoming lectures. Here is a list of references which is being used for the preparation of lecture. I hope you have enjoyed this one. I will see you in the next. Till then, take care. Goodbye.